having looked now at examples with systems of equations where we know what to do with two distinct real eigenvalues. That's all the examples we looked at. We've seen what their phase portraits look like, we've seen how to solve them, we've seen what the solutions look like. So the question now is, what if the eigenvalues are a repeated real value or complex eigenvalues? We're not going to do the repeated ones just for sake of time. It would add a lot to what we're trying to do, and it doesn't enlighten a whole lot. So we'll leave that out. So we're going to look at complex eigenvalues. What happens if we get complex eigenvalues? The development is a little bit complicated, but they don't call them complex for nothing. And once we get to the end, we're basically going to have a formula that's given on your formula sheet. So the process of actually doing one of these problems won't be terrible. There's just a little bit of development I have to show you. So if some of this is messy and you feel like it's not making a lot of sense, don't stress too much. As long as you can work out the problems, that's what we're interested in for now. Obviously, it'd be ideal if we would be comfortable with the theory, but we live in the real world, so we'll take what we can get. All right, so let's take this one and start doing what we've done before. To find the eigenvalues, we're going to take the determinant of A minus Ri. So these diagonal elements get an R subtracted from them, and that has to equal 0. So taking this determinant means we multiply -1 minus R and -3 minus R, then multiply 2 and -1, subtract, and then all has to equal 0. All right, so multiplying this out, what you end up with is R squared plus 4R plus 5 equals 0. And if you try to factor that, you'll get frustrated very quickly. So instead, if we go to the quadratic formula, you should find that R is -2 plus or minus I. And I'll leave the details of that to you to do on your own. But there you get your complex conjugate pair values for R. So we've got two eigenvalues as before. So let's say we take -2 plus I over here, and then take -2 minus I over here. So if R equals -2 plus I, again, we're plugging this back into this matrix here, not the determinant, but the matrix itself. So we have -1 minus -2 plus I, so that would be 1 minus I. And 2, -1, then -3 minus -2 plus I gives you -1 minus I. So that times U1, U2 equals 0, 0. We can do the same thing on the right side. We'll kind of parallel this as we go. And I don't want to take a lot of time talking about this because it gets kind of tedious after a little while. But if you can do one of these, you can do the other. All right, we're going to see what happens as we come out of this. So on the left side, what this means is we don't need both equations. We're just going to take the first equation. So we have 1 minus I times U1 plus 2U2 equals 0. Now, for the sake of simplifying the numbers here a little bit, so I don't have to deal with fractions quite as much, I'm going to solve for U2. Well, I'll solve for U. Yeah, we'll solve for U2 to make this easier. Because if we solve for U1, we would have an I in the denominator, and that's just a little messy. It's doable, and you can work with it, but I don't want to have to pause and talk about what to do with I in the denominator and how to work with that. So just to avoid that, we're going to solve for U2 and then let U1 be an arbitrary value. Hopefully that makes sense, but if I'm going to solve for U1, I have to divide by this, which I don't want to do. So it's easier to solve for U2. So U2 is going to equal -1 minus I divided by 2, so -1/2 times 1 minus I times U1. So then I can pick U1 to be 1 if I wanted to, but again, just to kind of avoid fractions, let's make this easier and let U1 equal 2. Again, that's an entirely arbitrary choice. You could let it equal 1, and that would be totally fine, but then you'd have to carry fractions around, and that's just, when we can avoid them, might as well. So if we do that, then u2 equals -1 minus I, or -1 plus I, if you distribute the negative. So then your eigenvector here, u1 is 2, and u2 is -1 plus I after you multiply out and distribute the negative. If you do the same thing on the other side, you'll get 1 plus I, so most of it is almost identical. Again, I don't want to spend a lot of time talking about this because it's almost exactly the same thing. So then again, we let u1 equal 2, and so then u would be 2 and -1 minus I. So notice that the form of these is almost identical. The two eigenvectors are almost identical, except that one has a -1 plus I, the other one has a -1 minus I. So you have two eigenvalues and two eigenvectors. Now, I'm going to skip some work for you, and I'm going to tell you that we only need one of these. When you're dealing with complex eigenvalues, it turns out through some convoluted algebra. If you're really interested, you could look at your textbook. I doubt any of you will. It's not something you need to know right now, but through some convoluted algebra, you can show that really only one of them is necessary. If you use both, you kind of just get to the same place you get to if you use one of them. So we'll just pick one and not worry about it too much. Kind of the idea here is that with the plus or minus I, it's kind of like if you remember what we did with second order equations that had complex roots. If we had something like r equals a plus or minus bi, all we were really interested in is the values of a and b. The plus or minus didn't really affect anything. We just selected out the real and complex, or real and imaginary parts, a and b. And we got something like y equals c1 e to the at cosine, and same thing with sine. So all we were interested in was the magnitudes of a and b, not so much the sign. That's kind of what we're driving at here, is that the -1 plus I or -1 minus I is not so important as the values that go here and the value that's the coefficient of I in this case, which is 1. That's kind of what it ends up looking like in the same way. So now, in this example, we have r equals -2 plus or minus I, and you can kind of think of there being a 1 here, right? And so this would be our A and this would be our B in the same way we did before. And we're still going to have e to the at cosine and sine, but the addition to this is that if you go back to the general form of these solutions, where do I have it here? Let's see, where you have all the way back here. This sort of thing here, where we had e to the r1 and e to the r2, that's where we're now going to have e to the at sine and cosine of bt. So that part will still kind of map to what we did with second order equations for kind of the same reason. So we'll include those there. And then the only question is what to do with u1 and u2. So that's the last remaining step, and that's kind of where we have to add in some formulas here. So the other piece to this is that u itself, the eigenvector, is composed of a real part and an imaginary part. So stick with me here for a second. If we look at our example here, we had u equals, what was it, 2 and -1 plus or minus I. So you could break this down as 2, -1 plus 0, 1, I. Notice how the top line doesn't have any I in it, so it's just a real part and then no imaginary part. And then the second line has a -1 real part and a +1 imaginary part. So in this case, this would be the real part of u, the real u vector, and this would be the imaginary u vector. All right, so if you're still with me, if you followed any of this at all, we kind of get to our conclusion at this point, and this is what will be given to you on the exam. The final answer is that x is C1. We have our two solutions, which I'm going to write separately, but they have kind of the same form. x1 is going to be e to the at cosine bt times the real eigenvector part minus e to the at sine of bt times the imaginary part. x2 is going to be almost the same structure, but it's going to be sine of bt times the real part plus cosine bt times the imaginary part. So obviously the reason I'm giving this on the exam is that I don't want you to have to memorize which one goes with sine and cosine, which one's positive, negative. All that's just kind of wasted brain space when you can look it up in real life, obviously. So you can probably tell that I'm skipping some steps here. There's some algebra that I'm avoiding. It would just cause more trouble than it's worth to show you all that. So the important part is that you get to this conclusion here. So as far as the problem itself, you would solve it just like we've done before. You'd find your eigenvalues, and once you recognize that they're complex, you can just pick one of them and find the eigenvector that goes with it, and the other one will be kind of the mirror image of it. And then once you do that, you'll break it down into the real and complex, or real and imaginary parts, and those go here and here. And then you obviously know what A and B are just from finding R, so those go here and here and so on. And then you're pretty much done. So solving one of these complex ones is pretty quick once you know what you're doing. It just looks nasty when you write the answer down. It's a long one, but once you do that, then it's not too bad. So in our example would be x1 would be, let's see, A was -2 and B was 1. Write that down. So we had R equals -2 plus or minus I. So that means A is -2 and B is 1. So our first solution would be e to the -2t times cosine of t times our real eigenvector part, which would be 2, -1. And then minus e to the at, sorry, a is -2. E to the -2t sine of t times the imaginary part, which is 0, 1. And then x2, the same form would be e to the -2t sine of t. It's kind of tedious to write this down, but it's mostly just copying and pasting. Plus e to the -2t cosine of t times 0, 1. And there's our solution. And then, of course, the full solution would be c1 x1 plus c2 x2. It's just they're long enough that I don't want to write them all on one line. I'd rather separate them out like that. So there's an example of a solution with complex eigenvalues and thus complex eigenvectors. And then we can think about what this system looks like. We're going to look at the phase portraits for one of these and see what that looks like as well, and how that relates to ones we've seen before. So let's take a look at the phase portrait for this one. It should be the same example. Yeah, it's the same example we just did. So if you look at this one, you'll see a stable spiral. And we saw an example of this earlier. We didn't have the language of eigenvalues to talk about it at that point, but there's this stable spiral where there's this equilibrium right here, and then everything is trending in toward that along these spiral curving paths. So the conclusion is that generally with complex eigenvalues, what you're going to see is a spiral effect like this. It could be either a stable spiral where they're all trending inward like this, or it could be an unstable one if they were trending outward like that. And the way you tell which one it is, if you look at the real part of the eigenvalue, you'll have e to the at, and that sign determines the source, the stability, whether it's a source or a sink. And it's the same conclusion as we saw with the real eigenvalues, if that real part of the eigenvalue is negative, it's a sink. If the real part of the eigenvalue is positive, it's a source. The same idea. So negative trends toward the equilibrium, positive trends away from it. So in our example, we had r equals -2 plus I, so A was negative, which is why it's a stable spiral, asymptotically stable, why everything is trending in toward the equilibrium. For an example of an unstable spiral, we can look at this one here. And I've already found the eigenvalues for this one. That would be 2 plus or minus 8i. Notice that the real part, which is what determines the stability, is positive, so it's going outward. So this one, the spirals are all trending outward. It's an unstable spiral. So you can kind of tell that just by looking at it, just by looking at the eigenvalues, whether it's going to be stable or unstable. As soon as you know that they're complex, you can expect to see a spiral, and the exact shape of the spiral really just depends on the values you have, but in general you can expect to see a spiral, and you can tell just by looking at the eigenvalues whether it's going to be a stable or unstable one. So the previous one was stable because the real part was negative, and you can see if you look at the solutions over here for x1 and x2, that things are trending toward 0 over time, versus in the other case, the unstable case, where the solutions start oscillating faster and faster and everything just goes crazy. So that's the unstable spiral. Again, the spiral part comes from the complex eigenvalues. The stability comes from whether the real part is positive or negative. If it's positive, it's unstable, it's a source, and if it's negative, it's stable, a sink. So that's what, in general, with complex ones. There's one last case I want to show you, this example here, where you have, as shown, the A matrix, and the eigenvalues have no real part. So there's 0 plus or minus 3 root 3i. So it's purely imaginary eigenvalues. And in that case, you'll notice that you get this, it's still kind of the idea of a spiral, but rather than a spiral itself, it's these ellipses, these circles, these loops that keep going around. And this is stable, right? This is a stable system. This is kind of like the Lotko-Volterra model we talked about with the population, the predator-prey model. It's the same kind of idea where it's circling around an equilibrium. And if you look at the solutions x1 and x2, you can see that where they're just oscillating stably, right? They're not going crazy or anything like that, but they're not settling down to any single value. They're just continuing in this stable pattern. So purely imaginary eigenvalues give you a stable equilibrium with solutions that look like circles or ellipses, like this one. And here's just a little note about what the equilibrium point is. As we've done before, you can solve that system and find where it equals 0. But every homogeneous system has an equilibrium at 0, 0, which is most of the ones we're looking at. So there's not a lot that's interesting about where the equilibrium solutions are for the examples we're interested in. The more interesting thing is what the solutions look like. So now that we've wrapped this up, you can go back and kind of look at some of the examples we've seen before and see if you can pick out, just by looking at it, what kind of eigenvalues and eigenvectors it has. And every time you solve one of these systems, you should think about, based on what you see with the eigenvalues and eigenvectors, can you imagine what the phase portrait is going to look like? And maybe sketch yourself a simple phase portrait and see if you can draw them just to get a sense of what's happening. A phase portrait's a very powerful tool to get a sense of what solutions are doing, whether they're stable, unstable, blowing up, going to nothing, etc. There's a lot of information you can gather from them, and they're relatively easy to draw once you know what we have seen about eigenvalues and eigenvectors. So that wraps up our study of systems of equations, and it actually wraps up the semester's work for us. So we've seen a lot, and a lot of it has dovetailed together, as we've seen even here.